SOCRADES is an innovative research project, partly funded by the European Commission, that pushes web service technology down to the lowest layer of embedded software with a focus on the industrial automation domain. The project brings together a unique consortium of three major competing companies in the field of automation technology: Schneider Electric, ABB, and Siemens. Further, SAP, as the global leader in business applications, ensures close coupling of manufacturing with back-end business applications. In strong cooperation with academic thought leaders and highly specialized SMEs, this project defines new methods in hybrid automation by integrating resource-constrained devices to powerful back-end systems using web services. Numerous communication standards exist today for the devices on the shop floor of a manufacturing company. Various protocols are used at different levels: between the sensors and actuators within a machine, among the machines that form a production line, and between product lines of a plant. Additionally, there is an integration gap between the production processes and the business processes of a company. Currently, this gap is addressed by proprietary connections using human integration, file transfer, or sending messages of homegrown formats. This creates inflexible interfaces that need to be maintained at high cost as the company adapts to changing market needs. Let's have a look at the production line of a multi-site manufacturer. One of the robots at that line recently suffered from a failure of the gripping tool, you could say the hand of the robot, which failed because of overheating. The production line had to be stopped for half a day until a replacement was delivered and the defect gripper had been exchanged. The global production manager learned about the incident only 2 days later via a phone call of an annoyed customer, whose high-priority order had been delayed. If the company had decided to deploy only web service-enabled devices at the production line and to integrate them with their business processes, the situation would have been better. Let's have a look at a demonstration of this concept. We attach a wireless temperature sensor to a replication of a welding gripper. This allows us to monitor the gripper's temperature and to stop the machine before a failure occurs. The temperature readings are provided via web services. A client running on a PC connected to the same network receives temperature data from the sensor over the network. Similarly, another web service is deployed on the controller of the gripper to control and update its status. We created a visual interface for the supervision of the production process to be displayed near the production line. A gauge displays the current measured temperature, and a graph visualizes the temperature history over a period of time. With the same tool that we used to create this visualization, we graphically modeled a rule that stops the production process if the temperature of the gripper rises beyond an operating limit. We also implemented a web application that allows a global production manager to supervise all production sites at a glance. The use of color coding visualizes the current status of each site at one glance. You can zoom and pan the map interface. To demonstrate the global web service collaboration, we simulate the overheating of the clamp using some high-end equipment, also known as a hairdryer. The rising temperature values coming in from the sensor trigger the rule. This stops the production process on time by invoking the stop operation of the production process web service before the gripper would be damaged due to overheating. The error is shown on the process visualization tool where the clamp status turns to red, and it is displayed on the production manager's overview screen. She can immediately identify the factory by color and tooltip notice. From there, she can jump to the alert history of that place, showing the errors that have recently occurred there, and get to the Resolution tab that offers actions to compensate for the problem. It shows the orders affected by the production stop. For each order, the production manager can choose to notify the customer about a potential delay by directly jumping into the customer account in the CRM software, to procure a substitute item if the order is really critical and the customer cannot wait, to create a maintenance order that will trigger a worker to take care for the task of fixing the situation, or to access the device's record in the asset management system that has all relevant contacts to the manufacturer to call for external help or guidance. In our demonstrator, we use, just like you would in a real setup, a robot equipped with a web service-enabled gripper that is controlled by a PLC and a SunSPOT, which hosts a wireless temperature sensor that can be programmed in Java. Both the PLC and the SunSPOT offer their functionality, that is sensing temperature, opening and closing of the gripper, as web services. We combine the fine-grained services from the gripper into a high-level service that encapsulates the production process, offering, among others, operations to start and stop the production and report events such as failures. On the backend side, we use SAP XMII, a product which runs as a service in SAP NetWeaver that allows you to visualize shop floor data and to graphically model and execute business rules based on that data. Our rule can be triggered manually or automatically based on events or changing sensor values from the shop floor, or periodically at intervals. The Production Manager's view was developed as a web application in Ruby on Rails, integrating Google Maps. To implement the device services, we used an advanced web service framework tailored for deployment on devices. It implements the Devices Profile for Web Services, or DPWS, which is a selection of web service standards, including WS Discovery for dynamic discovery of web services and WS Eventing for a publish-subscribe system for events. DPWS support is built into Windows Vista, so the services offered by the robot and the SunSPOT and the production process service are visible and accessible via Vista's network neighborhood. You just saw how web service technology on the shop floor can be used to tightly integrate shop floor processes with back-end processes. Such integration would be possible also with proprietary communication standards, but the interfaces would have to be maintained at high cost. Web services make the technical part of the integration trivial, abstracting from hardware, operating systems, and programming languages. In further steps of our work, we will investigate how different web service technologies tailored for manufacturing, such as DPWS or OPC UA, can be combined for maximum benefit. We will identify and trial further use cases for tight shop floor to backend integration. We would like to thank the European Commission, Schneider Electric, and Sun Microsystems for their support in developing this demonstrator. For more information, visit our website at www.socrades.eu.